Okay, so I want to take you through a case study from the book that has to do with Ruin probabilities. It's a case study that shows us something about how to do iteration and later also recursion. Um, and um, the main purpose of what I'm showing you in this video is how to deal with computations that become very long. Because of course when we have a very long computation, something that takes several hours or days, we need to worry about what might happen with the data that we construct using that grade, using that doing that experiment. So something unexpected might happen, like the computer could break down, or we could lose battery, or something like that. And we want to make sure that then, in that case, we don't lose all the data that we created. So the problem that I want to look at is a very simple-minded probabilistic question. So I'm asking, suppose that I have a gambler. That gambler goes into a casino and has a certain capital with him or her. So the capital we just call C, or capital. And then the game that's played is a fair game. So this is not a real casino. So you go in and you play, and then if you win, you uh, add 1 unit of money, and if you lose, you decrease 1 unit of money. So what we're interested in figuring out is, how probable is it that you'll go broke before you finish the number of games you intend to play. So we simply fix these two numbers, C and G, and then we say, suppose we play a fair game, G times, what is the probability that the capital goes down to 0? Because if you go down to 0, then you'll not be allowed to play again. So how do you figure this kind of numbers out? Well, instead of trying to do it with theory, we will try to do a um, simulation where we use pseudo-random numbers. And pseudo-random numbers is something that we're going to return to later in the course. But the idea is simply that we use some built-in procedures in Maple. I'm using this one called RAND, which will generate numbers, in this case either 0 or 1, with the same probability, and also distributed in such a way that you cannot tell it from something which is truly random. So this is far from random. You can see if I restart and do it again, I get the same thing out. I restart and do it again, I get the same thing out. So this is deterministic, but the point is that it's designed to be indistinguishable from something that is truly random. So that should work for what we're going to do here, and we'll come back to later in the course how you do something like this and all the pitfalls that are involved in trying to do something like that. Okay, so we will do uh, a number of small procedures calling each other that solve this question of how you figure out what the probability is that the gambler will go broke. And the first little program I called Ruin. And Ruin simply goes in and simulates one instance of this game. So we fix the capital, we fix the number of games, and then we simply play that number of games. And if the capital ever goes down to 0, we will say, yes, there was a ruin, the gambler went broke. And if not, we will return false and say, no, the gambler did not go broke. So a few things about this program. You'll see that I use a local variable called cap, and use that to keep track of the capital. So further down in the program, if I win, the capital will be 1 will be added. If I lose, the 1 will be subtracted. You may wonder why I'm not just using the variable called capital. And that's because in Maple, you're not allowed to change one of these variables that used to import data into a procedure. So the variables that you have up here after proc, you're not allowed to touch those. So that's why I need to use uh, a local variable to make the changes that I need to do to keep track of the capital. So that's just initialized to be the capital that I start with, and then I work with that. And now to make the simulation, there's a straightforward for loop. So this is a good instance of doing a for loop because I know how many times I want to do this. I've already decided how many games I want to play. So that's why I've chosen a for loop. But you can also see that this is inefficient in the sense that if my player goes broke before the end of G games, there's no need to keep on running. And actually my program keeps track of that. So if the capital at some point goes down to 0, then I will break out of the for loop by simply leaving the procedure. So I will return true, and then the procedure will stop running, so I will not waste time on the remaining games after the player already has gone broke. So that's an efficient way of not wasting time, and also fairly intuitive. But then down here you see the key lines that says I will take this random number, which is 0 or 1. If it's 0, then I say, okay, I won, my capital is increased. If it's 1, then I'll say I lost, my capital is decreased. And if I make it all the way to the end after the for loop, that means that I played that number of games but never went broke, so I will return false. So this is what the first little procedure does. It plays such a game, so let's try it. If I say ruin, I say let's say that I have a capital of 20 and I want to play 100 games. Then in this case, I did not go broke. I didn't go broke. I didn't go broke. I didn't go broke. So that seems to indicate that the probability of this happening if you have a capital of 20 is fairly low. But of course, in order to do this a little bit more systematically, of course, to figure out how many times you need to do this to have a certain level of precision, that's statistics, but we're not going there. We're just being sort of naive about this. But the idea is that, of course, we can do this experiment many times and see what happens. So the next little procedure called ruin frequency tries to do this little experiment a certain number of times. So we have still capital in games, and then experiments is a number of games that we're going to, a number of experiments we're going to do. There's a for loop in here that plays the game and says if we went broke, then we keep track of that in a counter called ruins, and then at the end of the program we return the probability as estimated by this simulation, the number of ruins divided by the number of experiments. So that's a simple-minded way of doing this, but there's one thing I would like to point out, and that is you can see I've organized this in 2 procedures. I could, of course, have put everything inside 1 procedure, but I would claim that this is cleaner because, first of all, I mean, I have smaller units. I can see that ruin plays 1 game and ruin frequency plays many games. Also, if I need to break out of ruin, I can do this very cleanly by returning. There is actually a break command that will allow me to break out of an inner for loop if I have organized it in 2 for loops. But that's a little bit messy. I think this is cleaner. So that's an example of this small units programming. And then finally, I will do something called ruin simulation, which is a little program to keep track of many experiments. So I will fix the number of games that I'm playing, I will fix the number of experiments that I'm doing, but I will vary the capital, say from 1 to 20. And if I do ruin simulation like this, then the point is that I will just go through the various levels of capitals, and I will play 500 games with that capital, and sorry, I will do 500 experiments with 100 games. And you can see, even though the numbers here are small, too small to make good estimates, I'm sure that statistician would say, still it takes quite a long time, right? And you can even see that it takes longer and longer because the more capital I have, the less probable it is that I will go broke. And of course, it's faster to go broke. If you go broke quickly, then you don't have to do the whole for loop, so you can save time. So I'm not going to keep this running forever, but the point that I'm trying to make is that this is something that you need to do for a very long time in order to get good estimates of the time that you need. And so, of course, I could just sort of make these numbers bigger and start Maple and go for a walk. But I would then run into the problem that, maybe something unexpected happens and I would then lose my data. So we will try to be a little bit more systematic about these things. And the best way of doing this is to use the file system. And this now becomes a little bit technical. So you can see this code here is not super readable, and I strongly suggest that if you want to do something like this, you just go in and cut and paste into your own program. But the point is that I'm using the file system built into Maple in order to put the data that I've generated into a file. So it's essentially the same program as before, but there's these fprintf clauses. So what happens is I open a file. That's sort of a call to the operating system on the computer, in this case my Mac here. So I ask the operating system to open a file for me that I can write into, and then I start putting data into that using some commands that, if you know the programming language C++ or C, this will look familiar to you. But it's various ways of organizing your data and putting it in lines and so on. So let me end. So the thing is that now I can do this little experiment, and what will happen is that I don't get any output to my screen. Everything is put into a file. So that means that, if my program unexpectedly dies, then I will be able to go in and look in that file and at least salvage some of the information. So I'll stop this video now and run the program, and then I'll come back in the next video.